That is the wrong page. There we go. That was silly. Oh, love that. Come on, man. Get your life together. All right. So, our bell work today was a review question from a hot minute ago. This is a graph of a something squared. And what I was hoping that we would use would be the ax minus h squared plus k, this guy. And our parent function of x to the x squared. So if we have our parent of x squared, that's when we pick our x's to find our y's. Which x's do we normally pick for our quadratic parent function? Where do we normally start when we're making a graph? In the middle. What is the middlest of our graph? What is the middle of our graph? 0, 0. We always started at 0 on our tables. We would take some bigger and some smaller. When we filled in our y's using our table or using our equation, our x squared, -2 squared is a positive 4. -1 squared is a positive 1. 0 squared is 0, 1, and 4. This was our parent function for the quadratic. That's not the piece we're graphing. We just use that to help us make the table of the guy we want, where we take our x plus h, and we remember how much graphing makes us yak, ya plus k, that guy. I would hopefully be at least vaguely familiar. What is the a for our equation we've been asked to graph? 1/2. Basically, we're just playing match 'em up here. So our a is 1/2. What is our h? Careful, careful, careful. Positive 1. It always has the opposite sign of the expression. So our h is a positive 1. And what's our k? Positive 2. So what we're going to do is we're going to take our x's and add 1. Our y times our 1/2 plus 2. So it's all about getting that parent table. The parent table doesn't change in between different quadratics, but each the parent table for quadratics is different than the parent table for absolute values, that kind of stuff. So these values change, but these ones don't, unless this does. So if I take all my x values over here and add 1, what are my new x values?
-1, 0, 1, 2, 3.
Gorge. The y's are slightly harder because we're going to take our y's. So I'm going to start with my 4 times 1/2, which makes it 2, plus 2. We end up right back at 4. Ugh. Well, it's what happened. It's weird, but it happens. Then we have our 1 times 1/2. So we have 1/2 plus 2, which means we have 2.5. So it is different. We just happen to have one that wound up right back where it started. 0 times 1/2 is 0, plus 2 is 2. We've already done the 1 and the 4. So before I draw these points, I'm going to ask us another question. What transformations do we expect to happen here? What should this look like? What does the a of 1/2 tell us is going to happen? It's going to compress. It's going to be like short and squished. How about this h of 1? What does that tell us is going to happen?
Right.
It is going to move right 1. How about this k of 2? Up 2. So let's see if that happened when we plot up these points. We've got our -1, 4, 0, 2.5, 1, 2, 2, 2.5, and 3, 4. Ooh, chunky. I've got a same size marker. So it should look something like this, which indeed has been squished. Looks like somebody sat on it. And for our locations, check our vertex here. It did go right 1 and up 2. So it used the transformations we expected. I wonder why I'm refreshing us on A, H, and K. Questions on this? Okay, once again, I'm going to put up a giant wall of text, which is me saying that we're using our curriculum. We are going to today talk about graphing square root functions. You do not need to write all this down. They want us to show it to you, blah, blah, blah. It has all kinds of information up here. Talks about our domain, talks about our range. The fact that this is not going to have symmetry because it looks like this. The important part for us to see here is this only has one arrow. This does not go off back in both directions. It is only going one direction. But honestly, that is what you need from this page. It is not a ton of things. We're just showing it to you to say we use the actual curriculum. Ta-da. We're going to start with our parent function. So naturally, the graphing stuff. Ooh, I should get the boxes out because I don't know how to use this. Alright, I will get the boxes out so I know I don't have the scissors or glue out. There we go. So when we're graphing things and we're using our A, H, and K, we have to have our parent function. So this is going to be the one we use the most frequently because we're going to use this to make all of our other graphs. So our parent function is really important. And this is when we figure out which x's we're going to pick to find our y's. Usually with like our absolute values, with any kind of other transformations we've done with our quadratics, we started in the middle and went either direction. I want us to think real hard for a second about if I put certain kinds of numbers here in my square root, I might not get an answer I can graph. What kind of things inside a square root are not going to give me a real answer? If I get negative numbers in there. So when we're picking values for our x's, we don't want any negative values. So I can start with 0. I could do 1, because I could do square root of 1. That's totally fine. If I do square root of 2, is that going to be pleasant, or is that going to be super icky gross decimal? Super icky gross decimal. What is the next number in my line that would not be super icky gross decimally? 4. If I wanted one more, what would be the next one? What would be the next non-super gross decimal? Yeah, it would be 9. So what we're doing is I'm picking out perfect squares here. This is the only time when we're picking x values for a parent function that we use not -2, -1, 0, 1, and 2. This is the only one. When it's square roots, we pick perfect squares. Because the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So when I plot those points, I want 0, 0, 1, 1, 4, 2, and then my 9, 3 is off the graph. It often will be. But we already said I can't go into the negatives. So this does not continue on. This is a stop point right here. My 0, 0, it's kind of like a vertex, but it's an end point. It is the end goal, stop point. Do not continue on. Do not pass go. Do not click $200. This only continues off to the right. But we cannot go into the negatives on our parent function. There are times we're going to have negative x's in our transformations. That's okay, as long as we follow our transformation rules. It's just in our parent function, we're never going to pick a negative x. So we picked these ones, the x's. To find the y's, I take my 0 and put it in here. 0. Square root of 0 is 0. That's where we get the y. F of x is just y dressed up in a fancy coat. So we're taking our x values, putting them in place of the x, and finding our square root. So the square root of 4 is 2. The square root of 9 is 3. What is the domain for this picture? Yes. So my domain is my x values, and they can be as small as 0, and they can equal 0, and they can go as big as I can possibly imagine. So this goes from 0 to infinity. How about my range?
0.
Same thing. Yep. 0 to infinity. We are going to use this parent table in the process of all the other graphs we do today. So questions on the parent table? Because A, H, and K are going to be how we do our transformations here. And A, H, and K have the exact same jobs they've had in every single other graph we've ever used them in. They work in the exact same way. They process the exact same way. We've just got to know where they are. And so our transformation form up here is very, very familiar looking. It looks a lot like the one for quadratics. And in fact, everybody lines up the same way too. I'm going to write the quadratics one just above it so we see it. Where we had our ax minus h squared plus k. Where our h is inside the PC. Our k is added on the end, and a is multiplied out front. It is set up the exact same way. So if we remember where to find a, h, and k in this guy, we can find a, h, and k in this guy. They are very, very similar. So looking at our equation over here where I have the square root of x plus 2 and then minus 1, what do we get for an h value? Gorgeous. H is inside our operation and will always have the opposite sign. So inside my square root and with that opposite sign. What is my k? -1. What is a? 1. It is multiplied out front. So it's an invisible 1. It's not any transformation. Nothing's happening there. But it is 1. So what transformations do we expect here? Which way should this move? Left 2, down 1. Yes. So we're going to start with our parent table. I'm going to take my square root of x. It's that same table we wrote on the last one. Where we have our x's and our y's. And we used our perfect squares for our x's. Our 0, 1, 4, and 9. That gave us our 0, 1, 2, and 3. And we're going to use that to make our transformed table. Where I take my x plus h, so I'm going to take my x's, and we're going to subtract 2. And then we're going to take our y's times a times 1, so it doesn't do anything, plus our k, plus -1, minus 1. So remember how we do that bit, how we set that up? Okay. I was just asking if there's questions. Remember this part? So then we're going to take our x's from our parent table and apply these transformations just like we did in the quadratic and the bell work. Oh, snap, relevance. Where I take my x of 0 and I'm going to take away 2. So we have -2. I'm going to have my 1 minus 2. So that's going to be -1. Yep, 4 minus 2 gives me 2. And 9 minus 2 gives me 7. Our y's. I'm going to take my 0 times 1 minus 1. So 0 times 1 is 0, minus 1 is -1. Then we're going to have our 0. 2 times 1 is 2, minus 1 is 1. 3 times 1 is 3, minus 1 is 2. So we're using our a, h, and k to help us figure out this part. So when we plot up our points here, I've got my -2, -1, -1, 0, 2, 1, and 7, 2 is going to be about there. It's off my graph, but only by a little. I cannot go farther left than the 0, 0 point, so this is my stop. So when I connect them up, I'm only going to the right. We do not put an arrow to the left on it. because we do not graph imaginary numbers on a real plane. There are ways to graph imaginary numbers, but it's not pleasant, and we're not going to do that. Honestly, that's what my grad school course is all about. We had to graph them, do circles with them, calculus with them. What's up?
Where did we get our formula for x minus 2? Is that just since x plus 2 and then y times y minus 2?
So this is the, I'm going to write it above, our x plus h and the y times a plus k. So just like we did with the quadratic in the bell work, it's that same pattern. I'm just going to pull that back up for a second. It's still this x plus h, y a plus k. It's the exact same jobs in the exact same way. So this is x plus h. So I take my x's and I'm adding h. My y times a plus k. So that's where we're getting those pieces. Good question. Good question. That help? So what's our domain for our transform function here? Our smallest value is -2. And what's our range? -1 to infinity. Our range is all about our y's. I'll put this pattern down with the table next time. I'll switch things around. Okay, questions on this first one? If we can do this, you are in excellent shape, because this is like, they don't really get worse. Okay. Let's do another one. So again, I have our transformation form up here, but if we know our quadratic transformations, we should be able to find our square root transformations. What is our A? I'm gonna put them way up here. Sorry, suppose. Our A is 2. That's this number out in front right here. What is our H? It's this guy in here, and it always has the opposite sign of the expression, so it's going to be a +1. What about our K? -3. Good. So what do we expect to happen? How should this move? Our H tells us it's going to go which way? H of 1. Which way will this move?
Right one.
Right 1. How about K?
Down 3.
Down 3. A of 2 means? It's not the vertex. It's a stretch.
It's more than 1.
It's bigger than 1, so it's going to be a big stretch. It's going to stretch it up taller. Part of that was just I wanted to have a big stretch. So our parent table stays the same. It's the exact same parent table we wrote for the last 2. So our parent function, it's our 0, 1, 4, and 9, with our y's of 0, 1, 2, and 3. The parent table does not change. We just use it as a tool. So when we do our transformations, and I'm going to put our little process over here as well. Where we take our x plus h and our y times a plus k. So we've already found our h, which was 1. So we're going to have our x plus 1. And we're going to have our y times our a, so times 2, plus our k, plus -3 or -3. So this pattern is the same that we've had before, and that's what we do to find our transformations here. So we're going to take all of our x values and add 1. So 0 plus 1 is 1. 1 plus 1 is 2. Whoa, that's a big 2. Try that again. Slightly more singing in size. 4 plus 1 gives us 5, and 9 plus 1 gives us 10. The y's are usually where it's slightly more challenging because there's 2 pieces. You could always use a calculator for it. So we're going to take our 0 times 2, which is 0, minus 3, which is negative 3. 1 times 2 is 2, minus 3 is negative 1. 2 times 2 is 4, minus 3 is a positive 1. And 3 times 2 is 6, minus 3 is a positive 3. That one's off my graph, but I'm still finishing out my table anyway. So we use these on these to get our current graph. So those are the points we're going to plot up. I'm going to take my 1, negative 3, 2, negative 1, 5, 1, and it's off the chart. I cannot go farther left. It's going to look like that. And we do see that it has been moved right 1. It's gone down 3. And that's been stretched up. It is taller. What is our domain on this one? Our domain has everything to do with our x's. Our smallest x is 1, and our biggest? Infinity, as big as I can imagine. How about our range, our y's? Negative 3, good. To infinity. Our h and our k will always be involved in domain and range. Always. Okay, there's only one more transformation we haven't really done, so we're going to do one more graph and that's it. So a little baby transformation here. So here's our last one that we're going to do. This is our 4th graph. Because we're flying through these. You guys are doing awesome. So we've got our negative 1/2 square root of x plus 3 plus 2. So I'm going to start with finding my a, h, and k. What's my a? Negative 1/2. What is my h?
3.
Careful, careful, careful. Negative 3. It is always, always, always the opposite of that expression.
I didn't see that.
Yeah, yeah.
I thought it was a minus 9.
You're good. You're good. I was like, when it's on your paper, it's a lot easier to see that. I know the looking up and down between the screen and your paper is a pain in the butt for that. What's our k? 2. Gorge. And if that was to happen on something like a quiz or a test, and you wrote down your A, H, and K like this, I can see what happened and where the mistake was, and it makes it so that I can find other points, things that you've done right. By writing things down, I can follow your brain and your train of thought. So please do that. It makes it so much easier for me to give you points. So also, stop erasing stuff on tests and leaving things blank instead. Drives me nuts. Our parent function stays the same. It's that same guy we've used every time where we pick our perfect squares for our x's because square roots are annoying to calculate. So we have 0, 1, 4, and 9. And our y's are our 0, 1, 2, and 3. Parent function does not change. It's the same for every square root. So we're going to do our transformation table over here. We're going to take our x plus h, y times a plus k.
So, x plus h would be x minus.
Correct. X minus 3. And our y is going to be y times -1/2 plus k plus 2. What do we expect to happen transformation-wise here before I start filling in the table? What does my h do? My -3. Which way is that going to go? Left 3. How about my k of 2? Up 2. How about this a of -1/2? It's going to be compressed, so squished. And since it's negative, it's going to reflect. It's upside down. So let's see what that looks like. So we're going to have our x's, and we take away 3. So 0 minus 3 is -3. 1 minus 3 is -2. 4 minus 3 is a +1. And 9 minus 3 is 6. That's the easy side. So our y's, y times -1/2 plus 2. 0 times -1/2 is 0, plus 2 is 2. 1 times -1/2 is -1/2, plus 2 is actually 1 1/2. -1/2 plus 2, it's the same thing as 2 minus 1/2. So it's either 1.5, 1 1/2, you could put 3 halves. However you want to put it. Yes, dear.
So what if it, I can get them. So what if you put like into a decimal to calculate? Like if you decide to.
That's fine.
Oh, is that negative?
It's negative.
Okay, so if we do -1/2,
Mm-hmm.
or we change that to 0.5.
Uh-huh.
Plus k.
Totally fine. You should get the exact same answer. It'll probably just spit out 1.5. So then when we do it with the next few, 2 times -1/2, that's going to give us -1, plus 2, which is a 1. And then on the 3, 3 times -1/2 plus 2, it's going to be -1 1/2 plus 2, we get +1/2. So when we plot up our points, -3, 2, -2, 1 1/2, 1, 1, and 6 1/2. Oop, that was a bad connection. I'm still doing it badly. It's so squished, it's really hard to draw it. There we go. Trying to hit all my points. But that thing has been squished. It looks very, very short. Somebody sat on that thing. And it has been reflected. It is upside down. It has gone left 3 and it's gone up 2. What is our domain of this one? -3 to infinity. My smallest x is -3, and it keeps going to the right forever and ever and ever. What is my range? It's between 2 and -infinity. This is going down. We always list smallest to biggest. So my smallest is -infinity. And my biggest is 2. Smallest to biggest. So again, my h and my k are involved in my domain and range. My domain will always be h to infinity. My range is either going to be -infinity to k or k to infinity, like the previous two have been. So when it's upside down like this, that means our a is negative. So these graphs don't get worse. That is as bad as they get for square roots. Okay? Oh, I just corrected it 4 times. Questions on that? Yay! We'll only 2 more homeworks after this. Like for the semester. This is your third and the last homework for me. There's 2 more after this. For the semester, like yes, that was fine for the, and usually I think the on or put it under the lid. Just so don't have to leave it a little flat. Yes, dear. Oh, I'm so good at counting. I'm the best at counting. That happens every time I pass it out, at least in one class, usually more than one.
I'm not engaged. I'm not. I wasn't talking about you. I thought you were. Bro, hold on.